Okay guys, so let's talk about section 5.2, optimal decisions in games, right? So in the previous section I kind of gave you a mini preview of what this section is going to cover, right? And when I was going through and talking about how one player has to take its move, and then it has to take into consideration when it's making that move what the other player is doing, and so forth, right? So let's go on. Let's build on this and then introduce an actual formal algorithm for this approach to figuring out what type of a move or which move the AI should take in an adversarial environment, right? So an optimal search in this context is going to give you some action sequence that's going to end in a terminal state where you've won, right? So the AI is trying to search for a move. It's going to go through the entire search algorithm that we're going to look at here, and then it's optimal, right? The result is optimal if you've got an action sequence where you've got a terminal state that's a win, right, for the person doing the search, in this case the AI, right? So when you have adversarial searches, there is some other agent that is going to be impacting the search. So in the context of Max and Min, if Max is trying to do a search, trying to figure out what move it should take, then its opponent Min is going to mess with that search. It's gonna impact it. There's gonna be some things happening in that search that otherwise wouldn't happen if there wasn't an adversary, right? So in response to anything that Min could do, any moves that Min could take in response to a move that Max could take, Max has to figure out a contingent strategy. So what is this? What does this mean? Max is going to have an initial move, and then it has to come up with all the moves in response to every Min counter move, right? So essentially, you're virtually playing the game out in your head, right? So the AI is saying, all right, if I choose action A, then my opponent could do action B. Well, in response, I would do action C. Well, in response, then my opponent would do action D. Well, in response to action D, I'll do action E. Well, in response to action E, my opponent will do action F. Well, in response to that, then I'll do action G. Oh, is that a win? Awesome. Then I'll go ahead and do action A because it led me down that path to a win. Right? That's kind of the way that this thing is going to work. So Max is anticipating its moves, all of the moves that Min's going to make, all the counter moves, and then Max is going to be thinking about the counter moves, right? So this is going to go on and on and on and on and on. So this is very similar to the and/or search algorithm that we looked at earlier, right? So Max is going to be taking the place of or, right? So the or nodes are going to be Max and the Min nodes are going to be and. So one way you can think of this is that an optimal strategy is going to give you outcomes that are at least as good as any strategy if you assume that you have a perfect opponent, right? So strategy I come up with, the move that I choose to make, right, it's going to be as good, if it's going to be optimal, if it's going to be at least as good as anything I can come up with, assuming that my opponent made all the perfect counter moves, right? So the AI has some strategy, going to have to choose a move. It's going to be an optimal move if the outcomes of that move are at least as good as anything else, assuming that my opponent doesn't make any mistakes. So how do we find that strategy? How do we find that solution? How do we determine what that move's going to be? Now, even just tic-tac-toe, as simple as we know it is, in terms of games, even that is really kind of complicated. So for the example in figure 5.2, just imagine a game tree that has two plies, right? So regular old triangle, right side up triangle, those are representing, quote, max nodes, right? So nodes in this context are really, they're virtual, right? So these things are being created, something that we're referring to as max nodes are being created in the recursion tree. Okay, so in this figure, those right side up triangles, those are representing possibilities for Max's move. It's Max's turn to move, right? So the upside down triangles, those are Min's nodes, right? So the terminal nodes, and those are all the nodes at the bottom, those are labeled with 3, 12, 8, 2, 4, 6, and so on. Those are labeled with utility values from Max's point of view, okay? From Max's point of view. The other nodes, those guys are being labeled with their minimax values, right? So you can see node B there labeled with 3, node C labeled with 2, and so on, okay? Now, from this tree, when this search is done, we've only got a couple of moves, right? A can take a turn, and then, or excuse me, Max can take a turn, and then Min can take a turn, right? So Max has to determine, given state A, should it take action A sub 1, A sub 2, or A sub 3, right? Now, when it makes that decision, it has to take into account, as part of this search tree, Min's possible responses, right? So if Max decides to take action A1, right, then Min in response could take actions B1, B2, or B3, right? Now if Max takes action A2, then Min could take actions C1, C2, C3 in response, right? If Max decides to take action A sub 3, then Min could take actions D sub 1, D sub 2, D sub 3, right? Now, the long and the short of it is that Max's best move, right? If Max is the AI, right? Its best move is going to be to take A1, right? And the reason for that is because that's going to give it the best possible outcome given Min, its opponent's possible moves, right? So if the AI, Max, decides on action A1, then Min, in response, the AI's opponent, could choose between B sub 1, action B sub 1, action B sub 2, action B sub 3, whatever those are, right? Now if it chooses action B sub 1, that would lead to a terminal state that has a value of 3 for the AI. If it were to choose action B sub 2, that would lead to a terminal state which has a value of 12 for the AI, for Max. If it chose B sub 3, then that would result in a terminal state valued at 8 for the AI, Max, right? So you assume that the opponent for the AI would always choose that terminal state which would have the least value for the AI, for Max. So Min, the opponent, would choose action B1 in response to Max's, right, Max being the AI, Max's action A1, because that would be the move that would benefit Max the least, right? Action B sub 1 would lead to a terminal state valued at 3. That's less than the terminal state valued at 12, which would be the result of action B sub 2, and that's less than the terminal state, which would be the result of action B sub 3. So Min would choose to take action B sub 1 in response to Max's action A sub 1. Okay? Now, what if Max had chosen action A sub 2? Well, in response, min could choose from action C sub 1, C sub 2, C sub 3. Now it's going to choose that action which leads to the least valuable terminal state for max. And that would be the terminal state with a value of 2. Okay, now if max had chosen action A sub 3, then min in response again is going to try to choose an action in response that has the least value for its opponent, max. So of the 3, D sub 1, D sub 2, D sub 3, of those 3 actions, D sub 3 leads to a terminal state that is the least valuable to max, right? So A is looking forward and saying, well, if I choose A sub 1, what are the choices that min would have? Well, obviously min's going to choose the worst one for me, so that would be 3. If max decides or is thinking about this and says, well, what if I had chosen A sub 2 instead? Well, then min in response is going to choose action C1, which would lead to 2, right? So me taking action A sub 2 would only be worth 2 to me, whereas taking action A sub 1 would be worth 3 to me, considering what min would do in response. And similarly for action A sub 3, max says, well, what would min do in response? Well, min has 3 choices, D sub 1, D sub 2, D sub 3. Well, obviously min, if it's a perfect actor, if it's acting rationally, it's going to choose action D sub 3. So of my 3 choices, A sub 1, A sub 2, A sub 3, my opponent would choose an action that, from my point of view, if I choose A sub 1, then my opponent's going to be limited to choosing an action that's worth a value of 3. So that's going to give me my best result. That's going to put me in the best position given the options that my opponent is going to have, right? If max chooses A sub 1, then the only thing min can do is choose B sub 1. That's going to lead me to a state in the game with a value of 3. That's a lot better than if max had chosen A sub 2 or A sub 3, because if max had chosen A sub 2, then its opponent would choose a state worth 2, and similarly for A sub 3, it would lead to the opponent choosing D sub 3. So it's in max's best interest to choose action A sub 1, because that's going to lead it to a state, or it's going to limit the options for min to choose an action response that's going to lead to a state for max that's valued at 3. So the best move that max can take is action A sub 1, because of all the responses that min can take, right? That's going to leave max in the best position. Okay, so I already went through and explained all that to you, but on the next slide there's a summary of that figure, right? So max, starting off, has the choice. I'll just go through the slide and summarize it for you. Max can take moves A sub 1, A sub 2, A sub 3. Min can reply, right? Now the game in that figure ended when there was 1 move taken by each of the players, max and min. So the game tree, 1 move deep. That means there's 2 half moves. Well, what does that mean? Well, a half move is, well, you know, max is deciding it's going to perform some action, and min's going to take an action in return, right? So each one of those half moves is called apply. Now the terminal state has utility values of 2 through 14, right? So take a look at all of the terminal states as represented by the bottom level, all the leaves in the tree, right? And so you have, 2, 3, 4, 5, 6, all the way up through 14. Okay. All right. Now this is going to be a recursive algorithm that we're going to look at, right? So again, try to understand, what's going on at a high level, and then trace through the algorithm, right? This is a really simple algorithm, but the only thing that makes it hard, and it is hard because recursion, right? Recursion always throws a wrench into things, right? And so it's important that you understand the recursion and have a good feel for the algorithm, right? right? So I'm doing my best by putting these videos together, but it's tough to know how well I'm doing with the explanation without having the live feedback from you. So I just want to encourage you, if you're confused at all, give me a holler, send me an email, or stop by my online office hours, okay, on Blackboard, right? So anyway, want to find that optimal strategy, okay, and how? Well, we're going to try to find, this should say Minimax instead of Min-Max, but, right, because the algorithm we're going to look at here is going to be called the Minimax algorithm, okay? So they made a little mistake on the slides there, but anyway, so let me continue explaining this. So want to find the Minimax value from each node, right? So that's going to be the value that is going to be representing how valuable a particular action is when playing out the game virtually all the way through all the possible terminal states, right? Like in the previous figure. So we need a function, should be called Minimax. Okay, and the value is going to assume both players are playing optimally the entire game. They're not making any mistakes. Okay, they're always taking the move that's in their best interest at that time. Okay, so the Minimax value for one of the terminal states. Remember what a terminal state is. Terminal state is just there's nothing else. It's over. Game over. Right? That state represents a state in the game that would be the end of the game. So that Minimax value, it's just that state's utility value. Right? So max is always trying to decide on an action that is going to provide a maximum value for this. Now min, which is the virtual opponent for the AI as it's going through this search, is always trying to take an action that has the smallest value, right? Because when max takes a turn, right, min in response wants to make the move that's going to be the least beneficial to max. Okay, and this is just going to be repeated over and over and over again. Okay, so here's a definition for function Minimax. Right, so what do we have? We have a utility function for a state, right? And we're going to need that if that state is a terminal state. Okay, we're going to need to find out what the maximum value is of all the possible actions, right, that can be taken. Let's see here. So you're going to see, right, if player S is max, right, and we're going to try to find the minimum value of all the possible actions if the player is min, right? So we're going to have a player function that's saying, okay, which player are we talking about in this particular state? Is the state a terminal state? What's the value of that terminal state? And we have to figure out what the maximum value is of a particular action from max's point of view, if it's max's turn, and what's the minimum value of an action from max's point of view if it's min's turn. Okay, now max is going to do even better in this algorithm. If min makes mistakes, max is going to reap those rewards. Okay, all right. So for example, to start off, Minimax, the best Minimax decision for max is A1, right? Min's best response is B1. Okay, so going back to that figure, right? What was the best action that max could have taken? A1. What was min's best response? B1. Okay, because from min's point of view, that's the minimum value, right? So B1's value of 3. Okay, and so for max A1, that 3 being returned, that 3 for that particular choice that min could have made in response to A1, well, the max value of all the alternatives, A1, A2, and A3, for max is choosing A1 because that leads to a value of 3. And then for each situation, each response to A1, A2, or A3, the best value that min could have chosen would have been 3 in response to A1, or 2 in response to A2, or 2 in response to A3, right? So that's kind of how that works. All right, so Minimax algorithm, that's what we're going to look at. Look at the algorithm now. So this thing's responsible for finding that minimax decision for the current state, that minimax value, right? So we've got recursion, Each of the individual pieces of the algorithm, simple on its face, it's the recursion that's going to throw it for the loop. It always is, right? But it makes sense once you trace through it a few times, because you're just doing this over and over and over again, right? So, what if in figure 5.2 these weren't terminal states down here at the very bottom, right? Well, then you would just recursively continue on, okay? So let's go take a look at the algorithm, right? So what's going on here? What's happening, it says in the textbook, it says the minimax values are backed up through the recursion tree, right? So all that means is that each function is just returning the value that was returned to it, okay? So when you were doing searches, binary searches on a search on a binary search tree, right? And you finally reach that terminal node. You finally reach that leaf. And your function returned true or false. Well, what happened? That true or false had to be backed up through the entire recursion tree, right? So a function was waiting for a function, was waiting for a function, was waiting for a function that got to a leaf, and then that function returned false to the function that called it. That function in turn returned false to the function that called it. That function then returned false to the function that called it. Right? So that's what the text means when it says backed up through the recursion tree. Okay. Now this algorithm is doing a complete depth first search. Okay, so some numbers here for you. You got a depth of m, and there's a possibility of b moves at each point. Time complexity, big O of b to the m. Space complexity, big O of b to the b times n when generating all those actions at once. Or big O of m if each of the actions get evaluated one at a time. Now, here's a very important thing to remember. Very, very, very important. Underline, underline, highlight, underline. When playing games, real games, the time for this, horrible. Horrible. Right? So, if you got an assignment or you're trying to write a program that uses this algorithm, even for something as simple as playing tic-tac-toe, it can take forever to play out a turn for the AI to make a decision. It can take minutes of real time because the search tree that's getting generated is ginormous, right? So anything you can do to cut down on the amount of time that takes is a good thing. Doing an depth limited search, right? Pruning the tree, right? So we're going to take a look in the next section or subsequent section at this idea or this algorithm known as alpha beta pruning, right? So as it turns out, you can ignore certain subtrees because there's no possibility of those subtrees generating a minimax value that's better than some other subtree you've already looked at. So why waste time generating that subtree and searching through it, right? But also, depending on how you score terminal nodes, if, say, your options from Max's point of view is a score of 1 or 0 or -1 and always wants to take the biggest, well, the first subtree that returns 1, just go with it, right? If 1 means a win for the AI, for Max, they just take it. End the search right there. Good enough. Take that action, right? Every other possible move is, at best, valued the same. At worst, is a loss, right? Or is valued even less, right? So once you know you have a winning move, just take it. Forget about evaluating everything else. That can cut down the search time immensely, right? So reminder, if you remember nothing else, right? right? If I was in class, I'd be jumping up and down and making all kinds of crazy motions and stuff to try to stick that in your head. The execution time for this algorithm is terrible, 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 terrible. Right. That being said, here's the algorithm. I mean, it's a good starting point, right? We have to have a basis for discussion on how to do this, how to do an adversarial search, what it looks like, right? And then you can tweak it to improve performance. Okay. So here you go. So you got 3 functions that are defined as part of this algorithm, and it's depending on other functions, right? So let me explain it to you, and yeah, we'll just go from there. So anyway, so you got the minimax function, minimax decision function. So you pass to it a state, right? So let's say that you're playing a game tic-tac-toe, right? And it's the AI's turn, right? Well, there's the board. That board represents a state in the game, and so the AI has to make a decision. Where do I put my X? Right? Well, you pass the board as a state. That's what this argument means. That's what's in this parentheses. And this function is going to return an action for the AI to take. Well, which square should I put the X in? Right? That's kind of where this is going. So this return line right here, this just means, hey, give me the action, or return that action that has the highest value that is determined by what min would have done, by what my opponent would have done. Okay, so that's what this means. So here's comes the other 2 functions. You got 2 functions here. You've got one function that's being called from the point of view of the max player. Right? In my example so far, the tic-tac-toe player, the X player, the AI. Right? Now, function min value, that's being called from the point of view of the virtual opponent, or the opponent for the AI, right? So remember, in its mind, right, the AI is playing out a virtual game. It's playing out all the scenarios, right? So from its point of view, it's max. Its opponent is min. Right? So these things are going to be bouncing back and forth as the tree develops. Right? So minimax decision starts the whole thing off, passing it the current game board state, and it's going to return, hey, here's the action you should take right now for this turn, for the real game. Okay? So what move should the AI take in the real game? Right? That's going to be the result of a series of virtual games that's going to play out in its head. Okay. All right. So it starts off by calling the min function. That's why it says here min value, right? Because for every single action that Max could take, what are the responses? Right? What's the response that min could take? Right? So anyway, so we pass to the min function the value, and that's going to return that utility value, that minimax value. Okay? Now, it only returns a value if the state is a terminal state. That's what the terminal test function is doing. If it's a terminal state, evaluate the value of that state. Okay? Return it. Boom. Otherwise, this next line's right here. V is set to infinity, because that's maximally huge, whatever the biggest value could possibly be, biggest number. Now for each action that could be taken, there's that actions function, and from that state, do what? Go ahead and try to, what this is saying here is choose the smallest value for all of the states, for all of the moves that the opponent could take. That's what the max value function is doing, right? So the result of the state given a possible action, what's the biggest value there from Max's point of view? Let's compare that with the value we've got so far and choose the smallest one. Once you've gone through all of those actions, this function then returns the smallest value of all of the moves it can make given the actions that it's possible to do, right? So that value is based off of the smallest value we found so far for all of the actions that are the result of what max can do. Okay, so now the max value function just does the opposite, just scores it the opposite. So it starts off by saying, hey, I want to try to find the smallest value, negative infinity, right? If it's terminal test, return the utility value, just like min does. But the loop is a mirror of min values loop. Okay, so for each action that could possibly happen, evaluate the result of that action given the state that we've passed, that we're currently examining, from min's point of view, right? Let's pick the biggest of the values we've seen so far as opposed to min's value, right? So for each action, figure out what the value is of that action from min's point of view, and then if it's, we'll pick the bigger of what we've seen so far, that's what V is here, and that particular action we're examining right now. Okay, so that's how it's working. So this recursion goes on and on and on and on, generating all of the possibilities. Okay, all right, so next up I want to do you a little example of this. I'm going to trace through an example for you. So okay, so let's play this out, right? So tic-tac-toe game, right? And X is the AI, right? And it has to determine what move should it take, right? What move should it take right now, right? So you've got the real game, right? So you're keeping track of that somewhere in your program, right? So let's say that the state of the game at that point, I don't know, I'll just make something up, is something like this, right? And it's the AI's turn, and AI is X, right? So we're going to have to feed this state into the Minimax algorithm, to that Minimax function, and then it's going to go through and play out all the possible virtual games in its head, in memory, right? Going through and saying, okay, well, what could possibly happen, right? And it's doing this recursive thing where, okay, which action am I going to take? Well, I'm going to base that action off of all of the actions that min could take. And then min is thinking, well, what move should I make, given all the possible moves that max could do in return, right? So max is trying, right? In this case, max is X, which is the AI, and min is the virtual opponent, right? So that's the opponent, as the AI is playing out all these games in its head, right? So there's the games in its head, and then there's the real game. So anyway, real game, feed this state into the algorithm. Now, that state, right, max has to decide, well, what am I going to do? How am I going to play this out? Right? What action should I take right now? I can move in this square, or this square. What should I do? Right? So what it needs to do is find the utility value for the move that is the biggest that it can take, given what its opponent could do in response. Right? So what are the possible moves? Right? So remember action A sub 1, right? Well, that could be putting X in the lower left-hand corner. So that could lead to us putting X here, right? Action A sub 2, well, putting X there. Action A sub 3, putting X there, right? Now, if it were to take action A sub 1, Max is trying to figure this out at this point, right? What would min do in response? Okay, now this is where min takes over, right? If the action a sub 1 corresponded to x going in this lower left-hand corner, right? So now it's min's turn, right? So this state right here is fed into the min function, the min part of the algorithm. And min says, oh, okay, well, what are my possible moves that I could take in response, right? Well, it can put an O there, or it can put an O there. So, we'll say B sub 1, right? B sub 2. Right? Now, here's the thing, right? Very first thing that the algorithm is going to do, right, before it even gets to evaluating these actions, right? So let me back up a second. Before it even evaluates these actions, it says, is this a terminal state? Min would say, is this the terminal state? Right? A min function. Well, yeah, it is. 3 in a row, right? So that would mean that the utility value of this, let's say -1 is a loss for x, 0 is a tie, and 1 is a win for x, right? Well, terminal test, 3 in a row, that's the end of the game. So min would immediately return that utility value, right? So it's backing up that value. So the utility function would cause 1 to be returned, okay? So that part of the tree is done, that part of the search is done. So we would now move on to a sub 2, right? Now here, min can say, well, what are my possible moves, right? Given the fact that a sub 2 is an x in this middle square. Now min starts thinking, all right, well, what am I going to do? All right, well, this is not a terminal state. So now I can go through and consider my options, right? So one option is to put O there, right? Which would lead to something that looks like this, okay? Or the other option action would be to put O there, right? Now, neither of those are terminal states, okay? But those are the two possible actions that could happen. Now, here's where the recursion comes in, right? These guys are both fed now to the max function, and then max says, all right, well, what are my possible actions from here? Right? Well, one action could be C sub 1, right? And if I do that, right, then what do I have? Right? When that happens, when that state gets passed to the min function, terminal state, 3 in a row. So that returns a 1. The utility functions can return a 1. Now the other possibility would have been an action that ended up let's see here, that ended up, well, actually I see that that's the only action that was possible, right? Because if O is here, and then the response would be, by max, would be just to put x there. So there's really nothing, there's no other action here. So that's just going to return 1 back up the tree. Right? Now, the depth first search continues, backs up over here. Okay, and a similar thing is going to happen. Right? What's the possible counter move? Well, the only other possible counter move is to put the x there, right? So that's going to be another terminal state. That's another win for X, for max, right? So let's say that, let's call that action D sub 1. So that means that utility function is going to return 1, right? So in both cases, 1 gets returned, okay? And then 1 gets returned all the way back up the tree. It backs up, okay? Now remember, way at the very top of this recursion tree, you've got Max trying to figure out which one of these actions it should take, okay? Now what would action 3 be? Way back at the top of the tree, right? Because we've returned, right? The recursion has gone down these subtrees and it's over, okay? Well, it could put X right there, right? So that state would then get passed to min, okay? And min then would say, all right, well, that's terminal state. What's the utility value for it? Return 1, nothing else for me to do, right? And this is returning 1. Okay, so then the search is over. Now, way at the very, very top, right? That loop is flowing, is flying for max, right? And so here are all the options. Okay, what's the best value? Well, they're all ties, right? So the last one that was evaluated was action 3. So the way that algorithm is written, action 3 would be returned by the Minimax decision algorithm. So action 3, put the X in the bottom right hand corner, would be what would happen in the actual real game, thereby ending the game. Okay? Now, had a hard time following that? Don't worry, don't panic. You got the algorithm in the slides, in the text. You can also rewind the video as much as you want to follow it, right? You'll want to do this on your own as well, right? And I'm trying to hurry so you don't have to sit through this for hours and hours and hours. So, you know, if I wasn't 100% clear, again, shoot me up for, you know, through an email, or hit me up, you know, in online office hours. I'll be happy to go through it with you again, step by step. But anyway, so based off of this state of the real game that we fed to the Minimax algorithm, game's over, right? There's no way that this game doesn't play out with the AI winning, right? Which makes sense, because you know from playing tic-tac-toe, if you've got this state and you're X, the game's over, you've won. It doesn't matter what your opponent does, right? So now remember when I was saying, you know, previously, very important, remember this, very slow. We'll take a look, right? I said, hey, as soon as you identify a winning state, why evaluate anything else, right? Action A1 was a win for this given state. Then why even worry about the rest of these subtrees at all? Just take action A sub 1, right? So we'll go back and I'll bring the algorithm back up and show you a simple modification for making that happen. So here we are back at the algorithm. Now, you see this, the for each A in action state do, right? Well, V is keeping track for both min and for max, the best value you found so far from their point of view. Now, if you know that a win is 1 in the max value function, as soon as the max function here in the loop returns 1, just break. Return right now. Terminate the loop. Right? Terminate the loop. Okay? You don't need to continue the recursion by calling min value. Terminate the loop. That action, that value that's leading down, right? That part of the search, okay? You're done. You found it. You returned the win score. There's no point in continuing on with the loop. As soon as your max function, or from min's point of view, your min function, returns the value that indicates that's the best possible move, stop the recursion. There's no point in continuing, right? You've pruned your search tree, okay? That could speed things up immensely. Okay, so optimum decisions in multiplayer games. So this is easy, okay, to mention. So to explain. So if you understand what we've talked about so far, right? You know, we have a game, 2 players. Now you might have 3 players, you might have 4, you might have 5. Okay, so what happens there is instead of having a single value for each of those nodes, get a vector. Right? A vector of values, a list of values, a container of values, an array list of values, whatever, right? So what that means is that you're keeping track of the scores, the Minimax scores, from the perspective of every single player. So for players A, B, and C, some vector, some list, you got a value for that move, for that node, from the perspective of A, from the perspective of B, from the perspective of C. Okay, so what's that vector? What does that mean? You got values at each terminal node from each player's perspective. So you'd have to have that utility function return a vector of utilities. And that vector is what gets backed up through the recursion tree. And I'm saying vector, C++, right? But Python, list, Java, array list, or you can't really return arrays, right? In C++, but in Java you can. In Python or Lisp, you're returning lists. Okay. Right. So here's how that search tree could be modified. Right. Here's how it would look. Right. So first 3 plies, you got a game tree, you got 3 players, A, B, and C. Each node is labeled with values from the viewpoint of each player. Right. The best move is marked at the root. Right. So so you look through this tree, here's your nodes at the very bottom. From the point of view of A, that particular node represents a value of 1. From the point of view of B, it represents a value of 2. From the point of view of C, it represents a value of 6, right? And so on, right? So now, if it's C's turn to move in this tree, right? Or from C's point of view, I should say, right? Which move is it going to take? What's going to be the best move for it to go with, right? Well, if you're trying to maximize value, right? Well, it's going to want to go ahead and take the move that leads to this node here, right? Because from its point of view, that value is worth, or that move is going to move it to a state that's worth 6. Okay, so you're just having to take into consideration values of each move for each player. All right, so what about multiplayer games? You got alliances. You're playing Risk or something, right? Maybe online Risk. You got AIs playing Risk. Alliances can lead to complications. So, what do I mean? Well, you might have your AI make some decisions where, hey, player C, way too strong. So then A and B decide that they're going to gang up. And they're going to form some kind of an alliance, and then suddenly all their moves are going to be coordinated, right? So that definitely makes things more complicated. Textbook covers that in more detail later. So in the next video, we'll look at alpha beta pruning, and it's a way to speed things up in your searches, right? To cut out looking through unnecessary subtrees. That's a little bit more involved than the kind of hacky way that I suggested in this video for simple games like tic-tac-toe, right? It works for tic-tac-toe. Other games, not as simple, might need some more thinking to happen. And so the alpha beta pruning approach to doing that is what you would go with, right? Is something that you would need if you're needing or playing a game that's a little bit more involved.